why can't both include in electrostatics?
No, that's electromagnetism.
Oh, okay, never mind.
Okay, so to review, electrostatics, you have a, if you have a positive charge and a negative charge, this is the force between them. This is the charge of one, and the little q is the charge of the other. This is very analogous to gravity, right? You have a GMM over r squared, you have a KQQ over r squared. Really the only difference in this formula is that you're using charge instead of mass to calculate the force. There is another difference, but we'll get to that in a second. The field of this, just like a gravitational field is Gm over r squared. The gravitational, the electric field, which very confusingly is labeled E. Not energy. Not energy. Electric field. KQ over R squared, right? So if you have only one charge, it will emit a field out from it. Just like the Earth emits a gravitational field, so any charged object will emit an electric field. The field is kind of like, what would the force be relative to any charge we put in this place? Okay. I purposely erased the positive charge because the field is based on a positive charge, what it would do to a positive charge. Okay, so that's force and field. Okay.
It's the force of electrostatic or force of what?
Yeah, you could call it electrostatic force, yeah. Electric field, electrostatic force. Let's just take a second to label that. And this is... Okay. Could you tell me, with gravity, what is the potential energy between the two? Could you tell me that? Yes?
Yes.
Okay. There's an analogy here.
Q over R. But it's not negative.
Why do I not? Potential energy is always negative, right? Why do I not make this negative?
For fun. Who cares?
It actually is negative.
You have the negative charge.
Right. So if you have one positive charge and one negative charge, that creates attraction, right? And so this will be a negative potential energy if we leave it alone. If we don't put the negative sign there, then if this is attraction, it will be negative.
But as it gets closer, the potential energy goes up. Doesn't make any sense.
No, it's the opposite.
Right.
As it gets closer, it gets, this gets smaller, the number gets bigger, but because it's negative, bigger negative means less potential energy.
Yeah. I was confused because there wasn't a negative.
Yeah, there's no negative, but if this is negative and that's
Yeah.
positive. What if they're both positive?
It's gonna repel.
This is something we do not get in gravity. Right. We don't think.
What happens if you have two negative masses?
No, two negative masses would attract it.
So you only have positive mass. We think. Antimatter maybe. We don't know.
Prove it.
The math says no. The math says antimatter will behave in gravity just like matter does. But we've never tried it. We don't know. We can't do the experiment yet. But for IB Physics 12, gravity is only attractive, but electrostatic can be attractive or repulsive, right? So then this becomes positive. if they're both positive charges or if they're both negative charges. You have positive potential energy, right? It's a different situation. Because if you have, you should be going out to 0, right, at infinity. But if you put two things, it raises some really interesting questions about our universe, actually. If you take two electrons, you can hold your fingers like this if you like, and you push them together. What's going to happen as you put your electrons closer together?
They're gonna wanna leave.
You're going to be like, I don't like it, right? Why don't they like themselves? They're the same.
They're not narcissists like that.
Anyway, you put them together, they get really like, you let them go, and what happens? Fly apart, right? Until you get to infinity, and then they have no more influence on each other. So it's the opposite of gravity. So yeah, you can have positive potential energy with electrostatics. Okay, what about, and I'm gonna make a little chart here. So we have all our formulas. So I'm giving you a lot of formulas today.
That's okay, they're all in the formula booklet.
Yeah, that's true. But it's nice to be able to understand them. Okay. If you're like, this is a lot of letters and jumbled up stuff. Let's put them all together in a chart. And then you'll be able to use them. We'll try. Really, there's just force and energy. That's it. So let's do force here and energy here. So you have, and let's say this is the value of the force. So we have KQQ, oh wait a minute, I have to, F equals KQQ over R squared, yes? Yeah. And energy, which we'll call EP to avoid confusion, KQQ over R, yes. That would give you a value in newtons or a value in joules. You can also say the field. You can have a force field.
Whoa.
Yep. Which would have, we would call E in this case is KQ over R squared. So
What's
just
what's the unit for that?
this would be in newtons per coulomb. Newtons per coulomb. And then here you have an energy field. So this is a force field. Your energy field is KQ over R. What would we use for that, do you think?
Volts.
Yeah, that's right. This is potential. So this is like potential force per coulomb of thing that you put at this distance. And this is potential energy. Even though we call this potential energy, this is the potential of energy we would have for per coulomb of thing you put at this distance. Okay. Now, somewhat annoyingly, you can make 4 more formulas out of these formulas. Because you can say, okay, if you have force and you have field, what would I have to do to the field to make it into force? Yeah, I just times this by Q, right? So if I just go EQ, well, that's going to give me force, right?
Yeah.
And so these formulas that I'm making, they're all at the back wall there. I have it written as F over Q equals E. So that formula right there, you see the F equals KQQ over R squared? The first black and yellow one?
Yeah.
That's your normal force. And the one beside it is E equals F over Q. That E is not energy, that's electric field. Yeah. Okay, and then what would I do to V to get potential energy.
Multiply by small q.
I can just multiply by Q again, right? By the way, the big Q and the little Q, they're not different. They're the same Q's. I just make them big and small to show that they're different.
So how are they different? Sorry. They're both.
What I mean is like they're different charges, but they're the charge of each different particle.
Right.
But it's the same kind of charge. Does that make sense?
Yeah.
It's like if you have GMM over R squared, you could say GM1 M2 over R squared, right?
Yeah.
Or you can just say big G. I just do it like this because it avoids some subscripts. So it's the same with this one.
So
Okay, so V times Q is going to equal potential energy, right? So there's one at the back like this as well. It's, where is it? So you have the EP is KQQ over R, and you have, it's this third one, the third black and yellow one. So it's EP over Q equals voltage. Okay, what about this? If we're looking at the values, what would I have to do to say the potential energy to make it into force?
Divide by r.
Yeah, so we can do EP over R would be equal to force. Now, this is an interesting one, right? You can change this into FR, right? You could say F times R equals EP, right? R is distance, this is energy, right? Which is the same as the work you'd have to put in. This is really just force times distance equals work. You understand? So if you imagine you could grab an electron, let's say that this is positive, and you grab this electron and you pull it back, you would have to do some work, right? Like stretching a spring. The work that you put in would be the same as the energy stored in it. And so your force that you have to pull it times the distance that you pull it is the potential energy stored in the particle. And then when you release it, what would happen? Where does the electron go? Oh, you guys are tired. Don't worry, a couple more days left. If I pull an electron from a proton away and then I release it, what's going to happen?
It's gonna go back.
Right? And the kinetic energy would be exactly the same as the work you put into it, and the same as the potential energy stored while it's stretched apart. It's like a spring, right? Okay, so that's this, and then for this one, if you did V over R, that would give you E, which is this energy. No, this is electric field, right? Did I do that right?
Yeah.
What's V again?
V is the potential.
Is the potential different like U or V? Like I've seen people use both.
So,
It's almost always V.
Is it?
I don't think I've ever seen V.
is it equivalent to volts?
This is volts.
Yeah, okay. So,
This is volts.
yeah.
Yeah. Now, there's a nuance there because
I don't know.
so when we talk about voltage, when you hear volts, give me a sec, Luke. When you talk about volts, you're really talking about potential difference. So this V is potential, which is an energy field. When you say there's 120 volts coming out of the plug, that means the difference in potential from this slot to that slot is 120. So it's kind of like if you pick something up, you can say, well, it's the MGH is 10 joules. But really, that's the difference from here to here, right? It's the same with the V's. The negative side would have 120 joules per coulomb more energy than this side. It doesn't mean that the other side has zero energy. It's just that there's a difference between the two. And so if you have a difference between here, and I let this go, what's gonna happen? I get energy, right? And it's the same with the plug. If you plug something in, you have like almost a fall of energy from one side to the other. The electrons fall through the wire. It's very similar to gravity. Yes, Andy?
So does that mean that like at the end of the wire it'll like have more energy than like in the beginning?
No. It has energy to give as it goes through the wire. So it's almost like if I let this go, but then there was a spring at the end, and I went and it dropped and it hit the spring and squished it. That's kind of what the electrons are doing. Because they're creating light, you gotta remember, right? Or running a motor, or making a speaker work, or whatever. Yeah.
So you go on like that. Is that why that cord, like right there, that white one has like two cords? Like you see how there's like.
Yes, that's exactly why.
Makes
Yeah.
sense.
There's always two wires in a cord to a device because you have to have power coming in and power coming out. So the electrons have to have a way in and a way out. If I cut this in half and made a loop out of it, it would work just fine. The electrons would go in and they would run the fan and then they would come back. And I'll show you all that stuff more later. So how come there's 3 holes in a plug then? Not just... But sometimes when you plug it in, there's only 2, right? Yeah, the third one is ground, you're right. It doesn't have anything to do with the circuit. People call it ground in the circuit, but it's not really ground. Okay, Avina and Anushka are asleep, so I better quit. I've talked at you for far too long. Grab a G and Coley, I'll give you some questions and you can do some. Oh, I better put the questions up here. It's page 429, I think.
Ready to wake up? I just got it.
Do you want one?
Page 497.
Really?
Try those, and I'll come around and I'll help you. Is today fit?
No. This is a Tuesday.
Okay, stop. Stand up. Just shake yourself out a little bit. If you need a coffee, get a coffee. If you want to go for a walk, go for a walk. I talked to you for a long time, so I apologize. You have now 25 minutes to work away and, you know, all that stuff.